Excellent. Yeah. Well, thanks so much for the invitation to come and talk. And actually, thanks to Doug. He set up my talk wonderfully in terms of hitting a lot of the things that I wanted to start with to give some context for this, but also I think I may set up things nicely for Bob next too. So one of my roles at Eigenvector is to assess technology, new methods as they come out. So people will write to us and say, hey, so there's this new method. Can you assess whether it's useful? It's a new analysis technique. Tell me, how does this fit into existing techniques? How is it different from something else? And does it work any better? There's this publication that says this is just the most wonderful method ever. And how do I know? So the truth is there's an awful lot of methods out there that work really well for a set of data that may never work on another set of data after that. And in that problem is even more complicated when you're starting to talk about large data. And I'll also say there's another side to this, which is that there's an awful lot of really interesting work being done in the machine learning side. So the computer scientists are looking at a lot of stuff. And they're throwing out all sorts of interesting techniques that nominally should, excuse me, that are interesting, but they're also they're not very well driven by the underlying science. So as scientists, we have to approach things saying, okay, and Doug described this very well, you can take the data and try and develop these hypotheses, but you also have to then say, does that make sense from the scientific side of it? It's sort of looping it back around. And sort of the validation sense. And I see a lot of that doesn't work. And there's a bunch of great talks later in the conference where people are proposing, hey, I've developed another technique. I'm going to talk a little bit about some of the things that we look for when we're assessing whether a method is useful or not, and kinds of questions you should ask, and it deals directly with some of the stuff that Doug just did. So in general, I actually said in the title that I was going to talk something about preprocessing. I'm going to have a slide just so I can say I talked about it. But really I want to focus more on some of the multivariate analysis methods that are fairly well suited to the big data kinds of problems and that are being used currently by other communities too in big data. And I'm going to give two examples, one which has been published and many of you I'm sure have seen this, but talk about a couple of the methods with this as a reference point to describe how they're related. And then I've got my example 2, which is my secret data set, and I'll explain more about that in a minute. And then finally talk a bit about validation results. First though, and some of you may have seen this is a slide I borrowed from August Schmilde, who gave a course with us last year. But it's nice because it lines up actually, again, very similar to what Doug showed, that there is an awful lot that goes into the analysis of any of these samples, of course. I mean, we've got all sorts of aspects of developing the right biological question, appropriate experimental designs, appropriate sampling, the actual data acquisition. There's lots of things to take into account. It's a massive amount to consider there. I'm going to focus in fact, I'm not even going to really mention preprocessing, but I'm going to cut straight to sort of the data analysis side of that and talk about how these relate. So, like I said, just so I can say I said something about it. The fact is that a lot of the preprocessing, as a community, it seems like there's starting to be some very consistent conclusions about certain methods that seem to work, certain methods that make sense, involving internal standards, QC samples, when they're run, how they should be used to correct for instrumental effects, things like that. But also things like transformations, which desensitize you to some of the various issues of the data. And finally, missing data replacement, and there's some pretty standard methods. And so yeah, there I've said something about that. What I really wanted to go into is, and I did a first cursory walkthrough of some of the posters that were going up, because there are several methods that have existed for donkey's years, for very long, that are used by a lot of people. And they are also currently being used in a lot of the big data communities, but they're very well suited to this. And I bet everyone has probably at least seen these or is very familiar with them. The most obvious, which you see left and right, is principal component analysis, which is just a factor-based decomposition of the data. And so it's basically looking for correlations among my metabolites. And the thing about this, of course, we expect there to be correlations from a biological point of view, so that's obvious. A related technique that is not used as much, although it's been out, I think, for 10 years, is ASCA, which is ANOVA simultaneous component analysis, which is just an ANOVA followed by principal component analysis, and I'll talk more about that in a minute. And then sort of really one other technique, although it's often described as two separate ones, is partial least squares discriminants analysis, PLSDA, sometimes PLSD, you see the same thing, and orthogonal PLSDA, OPLS. And again, this is a factor-based method. It's just linear discriminant analysis based on factors. So it's a way of dealing with the fact that we've got so many variables. So let me jump back for a minute, because this is the other thing about the metabolomic data that's such a challenge, is that it's very easy to collect lots and lots of variables, of responses, of metabolites. We've got great instrumentation that can draw a lot of that out. Samples are really ridiculously expensive, especially because we do have to run lots of QCs along with our regular samples. And the biological aspects, the experimental aspects of collecting the samples. What this does is this gets us into a realm of data which is a real challenge from a numerical point of view, where we have what we often describe as short fat problems, so that the data table's not very long, not very many observations, but loads and loads of variables. And a lot of methods have trouble with this. These methods, by the way, are commonly used on data with 10,000 or more features. So these are used in those scenarios, but they can go awry, which is going to be the upshot of some of this. I wanted to put it into perspective. Everything I just talked about really are sort of multivariate methods. They try and use the relationship among the variables, among the metabolites together to draw conclusions. There are, of course, a whole slew of standard univariate methods that are often used. ANOVA, I mentioned random forest here. One can argue that this is actually a bit of it really is sort of a multivariate method, but it often is using individual variables one at a time. And lots of raw data methods. The biggest disadvantage is that you don't get as good signal to noise as you do if you can do a multivariate method. The other really big risk of a lot of the univariate methods is if you try and draw in lots of individual metabolites one at a time, you can overfit, you can start drawing apart things. Nominally, the concept of the multivariate is, well, okay, I can look for correlations, try and keep what's described as the dimensionality of the data small. Nominally, they should be safer, right? And this is totally going to be a drop here for Bob, but so Eigenvector does have commercial software that we put out. Our software is based in MATLAB. It is a open source in the sense that when you have it, you can see all of the code, which is a notable difference. I think it's important to recognize that knowing exactly what the numerics are doing is critical. But having said that, everything I'm showing is basically stuff that's in that environment. This is the first data set that I wanted to mention. And it's, like I said, this has been published in the past. They were looking at cabbage and the glucosinolates, which are, they were basically taking these cabbage plants, harming them. Did I say that right? I'm an analytical chemist, not a metabolomic person. So, so I'll admit to that and in the initial thing. But basically, the experiment was these plants are growing. They essentially treat them with chemicals as if they are being attacked. They did three different treatments. There was a control group where nothing happened. The roots were damaged and the shoots were damaged. 4 different time points. They watched them over time. 5 replicates of each of those time and treatment combinations. And this shouldn't say concentrations. This should say 10 measured metabolites. The idea is that they're looking to see what's going on in the biological system. How is the plant responding in terms of metabolites to this sort of attack? So the data, like I said, this has been out there, but the first thing that a lot of people are doing, let's do a PCA on it. Let's just look for whether we can separate out the different groups. So we have our scores on PC1 and scores on PC2. Each point in here is one of our individual samples. I've color-coded them by the control root and shoot. So this is the different treatment groups. And you can see that there is some separation there, but not an awful lot. Okay, well, part of the problem here is this still includes the effect of time plus other aspects. So there's a method that is an offshoot of this, which is the ASCA method. Basically, we've got our X matrix just like we had before. In this example, I'm going to draw it out as if there's just two factors, A and B, which actually I guess the previous one did have. It has a time and a treatment. So the first thing you're going to do is take that data matrix, and for each individual metabolite, you basically do in ANOVA. You look for what is the mean effect for our treatment for each individual metabolite and for time and an interaction. So what you end up with here is a matrix XA, which is, in this case, the 3 different treatments by all my metabolites. Take that matrix, whoa, yeah, that was not the way I was going. Take that matrix, do a PCA on it. The effect is that you get scores and loading, something that will tell you how that one part of the data is representing itself. You do that for each of the additional terms, the time and an interaction effect. The thing about this, the thing that makes it slightly different from a standard ANOVA is the statistics fall apart when you combine them this way. And so the problem is, how do you tell whether this is actually a significant effect or not? And so the simple solution is to do permutation tests on it to look for it. So if we do that with this data, here is the exact same data for just the treatment effect, scores on PC1 and 2, and we can clearly see a better separation there, right? So this is great. We are, by separating out both the time and the interaction effects, we can really see what's going on with the treatment. So I want you to focus on, first of all, the sort of horizontal direction here, PC1. You can see that the shoot group tends to be further out in this direction. And so we're nominally separating the shoot from the other two in the horizontal direction. Some of the root effect is in there too. If we look at which variables are contributing to that, pay attention just to this top plot. What we get out of this is something that says, okay, we have really 2 metabolites that are relatively significant in that direction. And so I can focus in on those. Now is the point where I go back to the biological side of this and say, does that make sense from a biological point of view? I'm going to ignore PC2, although you can see that there was a separation up and down, which is largely the root effect, and we can see what seems to be leading. Why is the root treatment different from the shoot treatment? So one more thing before I go back and talk about that analysis for a second is PLSDA. And PLSDA has also been commonly used in a lot of these sort of directed analyses, these supervised analyses. Fundamentally, it's like PCA, except for that it finds slightly different directions in the data. It still comes up with scores on 2 latent variables, and each sample being a score. But then it goes one step further, is it also, in that same space, it basically draws, it says, okay, which direction separates my 2 classes? And so I can draw in some sort of dividing line here. Now the next plot I'm going to show you is this plot. I got to use both hands here for a second. It's this plot turned on its side. Let's see, this way, turned on its side, uprighted. So you're going to see the blue points are going to be above the line, and the green are down below. So I've just rotated it. So I want you to note one thing over here. I have cross-validated on that y-axis. I'll explain why this is important in a minute. But PLSDA, same data, do that particular analysis. I can now ask the same question. Okay, I can clearly see separation of the groups. What is it that led to that separation? The top plot is actually the orthogonal PLS results, and I don't have enough time to go into great details about this, but I want you to know there seems to be an awful lot of metabolites that are contributing to that. The second and third are 2 different variable selection approaches saying which variables, which metabolites are most important here. And pretty clearly, it gives us the exact same answer I just got from ASCA. which is actually a really important point. If you have only two groups, ASCA and PLSDA are actually numerically identical. They're the same method, which is one of those overlap areas. With three groups, it does change it a little bit, but it's worth noting that. So, okay, great. Obviously, the three methods seem to be separating. It seems to tell us something about the metabolites, tell us something about the system. Let me show you my example number 2. In this case, it's 15 metabolites that were measured. It's a very simple design. It's one factor that we are controlling, just two different groups of that particular factor. There are 10 subjects in each group, and I'm not going to tell you anything else about it right now. Run through, because there's only two groups, I can only get a single score, so basically this is just sample number, or 15 samples. And you can see that there's a separation of the two groups, and you can see these distributions over here. And I can draw in a line that says, okay, it does look like I'm seeing some difference. And here's the PLSDA plot. Again, like I just said, PLSDA is actually identical to the ASCA in this case. But you can see if I do a build, I've got my group 1 and group 2, clearly separation, looks like there's one that's on the border. So this is great. All right, let's take this and, oh, I gave away my secret. Then let's publish it. The reality is, this data is random. This was generated just by simply generating a random matrix of 20 by 15. 20 samples by 15 metabolites. It's actually not even the short fat problem. This is actually still taller than it is wide. There's a real risk in using any of these higher powered methods to draw out the information and overfit it. The number of publications I've seen in various literature where this is actually the case are scary. Part of the problem, by the way, is looking at pure scores on these. There's really a better way to look at that, and I'll mention this because we see this in a lot of the, especially the biological applications. How do we know? Well, ASCA, I already mentioned, we can do a permutation test. We can also sort of look at the magnitude of effects so that that's not as strong or as certain. PLSDA, permutation tests, or cross-validated predictions. So, okay, so here's the table. This is the random data set. And if you look down here, you can see the effect. It's only 5%. That separation of those two groups in my random data was only 5% of variation. The effect of the overall residuals was 95% of that. But more importantly, more critically, the p-value here is 0.4, 0.46, 0.47. So I mean, there's no way this is significant. And if you don't look at this at all, you would have no idea of knowing. And that's not even in that questionable zone of the 0.05 situation. So going back to the original data, here's the glucosinolates. The effects here are much more significant. So that gives me, okay, it's more likely I'm seeing something. But more critically, the p-values here are 0.001. So much more likely. If we do the same thing, PLSDA, permutation tests, and there's some different statistics that come out in this. This is on the random data. None of these is even in a questionable zone. It's really obvious that they're not significant. So it's pretty clear that was a questionable model. The one other thing I was going to mention here for the cross-validated results, I mentioned the scores plot, and looking at that is really dangerous. And you see this in papers left and right. And I mentioned that this Y predicted, which is basically that plot turned on its side, you can see the separation of the groups. If in cross-validation you pull out some subset of samples, build a model from the rest, and apply it to the left-out samples and repeat that, these are the results you get. And it's really clear that it's not there. And if you're not looking at this, you are dangerously close to fooling yourself. Now, bringing this back around to the idea of developing new methods. No method is even worth looking at if you haven't done some kind of assessment of what its power is and how likely it is to overfit something. Because that is the #1 case. And I will admit that I did this too many times where I've developed a method and I said, this is tremendous. And it seems to be doing a great job. If you don't validate those, it's completely useless. And the So really, while these methods can be really useful in terms of capturing the correlations, they really have to do an honest assessment, and this really means essentially going in from the other side saying, I'm going to try to prove that this is wrong. Not just I'm going to try and do a simple thing. So thank you very much for your attention. I think that puts us right at 20 minutes.
Many thanks, Jeremy. Does anybody out there have any questions? I think we've got a question. We've got a couple of questions here. 2 seconds.
Hang on, he's gonna have a mic here. Okay. Would you?
There's one, and the second comment that I would like to do is you speak about linear methods. And now in biology we have discovered that sometimes linearity is not true. What we need is ratios or non-linear methods to understand this. So if you can comment on those two important issues.
I'm not sure I caught everything about the second question, but it was about basically nonlinear methods. I will say really short statements about both. Yes, absolutely, number of samples does tie into permutation tests. It's a real problem because there's only so many combinations that are actually reasonably significant. But that gets back to the whole question of the power of the overall design anyway. And Doug made that wonderful statement about spend the time and the money collecting better data, assuring that you've got a good design to begin with, so that you're not trying to deal with some tiny little set. Unfortunately, that isn't always compatible with the drive of getting things published. But as far as nonlinear methods, the number of situations that I found where truly nonlinear methods are necessary are very few. And the fact that a lot of these methods can approximate what a nonlinear method does, and in a much more stable way. Having said that, there's absolutely some situations where the nonlinear methods are important, but what you have to remember is they're that much more greedy, and they're that much more capable of finding, capable of exploiting, I would say, some of these difficulties about the data. And I will honestly say, Google is running into this. They are a great example where they've developed a bunch of models, and they seem to be having troubles because they basically took this dump everything in, build a phenomenally huge nonlinear model, and it starts to fail because they didn't wrap back around to prove the certainty of it. So that's a really brief statement on that. I could talk for an hour, but I won't.
One more from Roy.
Yeah, so since you discussed PLSDA and validation, so on PLSDA and validation, a lot of the community seems to like quoting R squared and Q squared. Would you comment on that?
R squared and Q squared? They are, in terms of as assessments for whether the model is decent. Oh, they are terrible. He gave me a thumbs up, so I assume this is what he was saying. Now, this is a really good point. The question about how well separated were those two groups that I had, and I can do this in one plot. Let's go back to, ignore the fact that this is actually a completely false model, but where'd it go? There we go. Ignore the fact that this is completely a false model built on, too low-powered data, high-powered data, I guess. The separation, whether this model is good or not, has nothing to do with how well my red samples predicted as one cluster and my green samples predicted as one cluster. It has everything to do with how well I separated them. I could have red samples that were clear up there. This model would be a great model. R squared and Q squared they assess how tight those clusters are, not how far separated they are. And it is a real issue. Having said that, this is something that if the community at large seems to think that this is the right statistic to look at, then you're going to have reviewers come back and say you've got to show this. And it's a real issue. From a statistical point of view, I think it's a terrible way to assess them.
Let's hope that gets taped.
That's right. This is being recorded. So there you go. My Google statement was too.
I think we've got one more for you, Jeremy. Just a sec. No, we'll have one more. We'll have one more. We may as well. Go for it. Go for it. Go for it.
It's regarding ASCA.
Yeah.
First is, if you have seen effect at 1%, but p-value is still below 0.05, how confident are you? And second, if you want to evaluate interaction effects and it's not balanced, then what would you do?
So regarding the small effect and significant p-value, I think that's one of those where you also have to go back and ask the biological question too. Does it make biological sense, the answer I got? Look at your loadings. As well as, because nominally what you could be looking at is if you've got and if you have a large design, if you've got a lot of samples, if you've done a really good job, and that is just a very small biological variation, you could have detected it. And we see this, we see this in cancer detection a lot of times. It's very small differences in a lot of biological variability. That is possible, but you do have to ask the question, did I actually do an appropriate design? I will fully admit I'm not as much of a statistician to be able to safely make a statement on that, which I think is what I will also defer to for the second question, which is that there is, what was the second question again?
Unbalanced.
The unbalanced and unbalanced in. Oh, it's a challenge. Yeah, I know of a couple of approaches that people are using, but I don't think I can make any good solid statement on it. Is my short answer.
Okay, thank you very much, Jeremy.